Here we look at the EulerPaths and Euler circuits for the directed graph and the necessary and sufficient conditions to have an Euler circuit and an Euler path. So to have an Euler circuit, this is going to be for a directed graph if and only if for every vertex the in degree is going to equal its out degree. Then we'll have an Euler circuit. We'll be able to come around and close it back up, somehow using every vertex, every edge one time. And that will be an Euler circuit. For an Euler path, this is if and only if the necessary and sufficient conditions. There exist two vertices, we'll call them S and T, such that its out degree of S is equal to the in degree of S plus one more. And then the in degree of the other vertex there is one more than its out degree. And the rest of them are going to have the same in and out degree for their own vertex. Here's an example that we do not have an Euler path, so that means, of course, we won't have an Euler circuit. I wrote down the degrees. Remember, we use the notation for in degree, this superscript of a minus sign, and the out is a plus. So how many edges are coming in to the vertex A? Well, just one. Going out is 1. So in degree is 1, out degree is 1. List the rest of them. You notice it does not satisfy either of the two theorems, so I'm not going to have an Euler path, and I won't have an Euler circuit, since this is a necessary and sufficient condition. Here's an example where I do have an Euler path, but I'm not going to have an Euler circuit. So if I'm looking at the in degrees and the out degrees, I notice that, so you're just going to look at these individually, and so this is just for E. Does its in degree match its out degree? Yes. This is for C. Does its in degree match its out degree? Yes. A, in degree matches its out degree. And then the rest, the other two, we're hoping that it satisfies this condition here, where I'm going to have it one more. So the out degree of one is one more than its in degree. The in degree of the other is one more than its out degree. And it does satisfy that with B and D. The in degree of B, so notice the in degree of B is 2, and 2 is equal to its out degree, which is 1 plus 1. And then for D, it works for the out degree. The out degree of D, which here is 2, that's equal to the in degree 1 plus 1. And we already checked that the rest do have the in and the out degrees matching. So that means I am able to come up with an Euler path, just not an Euler circuit. So for this one, we should probably write this down, what would an Euler path be? So I want to start here actually somewhere where I can, like D. So D here, since I can go one way, and then, I have options from there. So I'm going to go D to E, so that's going to bring me then to A. So D to E to A, then that's going to bring me to B. Then from B, the direction I have to travel to C, can't go to D. And then from C to D, so notice I'm coming now into D, but I'm able to go out up to B. So we've traveled along each of them one time. Let me verify that. So starting at D, I'm going to go to E, then to A, to B, C, D, and then B. And we started here at D, where we were able to have some escape routes, going out and then coming back in and then out. In an Euler circuit example, so that means, you'll have an Euler path if it's an Euler circuit, but we look at the degrees again. Does it satisfy those necessary and sufficient conditions? So this is a nice way to determine if you do have an Euler circuit, rather than just trying to play around with it to see if you can come up with one. Well, let's see if there really is one, and then we can figure out what it's going to be. So looking at these degrees, I have the same values for that degree. In and out are the same there. The in degree and the out degree are the same for C. D has the same for its in and out, and so does E. So every vertex, its in degree equals its out degree. So that is called an Euler circuit. I can find an Euler circuit. Okay, well, what is that? So we look at this, and the Euler circuit, here's an example. Again, I'm going to start up here somewhere where, you know, I have more edges, ins and outs to choose from. So I'm going to start at A. So I'm going to start here at A. And then from A, let's go down to D. And then D, I decided to go to E. And then E to A. Okay, that takes care of that part, so we won't have to come back to that triangle. And now I'm at A. So A, I can go over to B. And then from B, I can go over to D. And then D to C. And then C to B. So that takes care of that triangle. And then all that's left, now I'm at B, I can come all the way over to A. Okay, so as you're choosing these, you just want to choose where you have your edges so you can come in and go out and make sure you, and it might take you a little bit of time to come up with the correct path, and that's okay, but there's some algorithms that we can look at later on in the book.